It formed in the dark. Not the dark we talk about, and not the absence of city lights or the shadow behind a cloud. The dark before stars, before heat, before any of the machinery that makes stars possible had assembled itself into the universe. And yet, there it was. HD 140,283 is a real star. It sits 190 light-years from Earth, or close, by cosmic standards. Close enough that we have measured it with precision instruments, run the numbers multiple times, cross-referenced the data with independent teams on separate continents. The measurements agree. The star is approximately 14.5 billion years old. The universe is 13.8 billion years old. Let's be precise about this. That is not a rounding error. That is not instrument noise or a margin that collapses under scrutiny, even accounting for the full uncertainty range in both measurements. The star's lower age boundary still presses uncomfortably against it, and in some calculations, past the accepted age of the universe itself. A star that is, by the numbers, older than the place it lives. Astronomers call it the Methuselah star. The name is almost too gentle for what it implies. Here is what a star needs to form: hydrogen, gravity, time for that hydrogen to compress under its own weight until nuclear fusion ignites. That is the basic recipe. That is how every star in every galaxy in the observable universe came to exist. But in the early universe, the first few 100 million years, there was something else missing. Something that makes the existence of HD 140,283 quietly impossible. Metals. In astronomy, anything heavier than helium is called a metal. Carbon, oxygen, iron. The periodic table below helium. All of it is what astronomers mean when they say metals. And in the early universe, there were almost none. The Big Bang produced hydrogen, helium, and trace amounts of lithium. That was the complete inventory. The rest had to be forged inside stars, distributed through supernovae explosions, recycled across generations of stellar birth and death before heavier elements accumulated in any meaningful concentration. HD 140,283 has almost no metals. That is, in one sense, expected for a very old star. Ancient stars are metal poor. This is consistent. But here's the problem. The star's metal content is so low to a fraction of a percent of what our sun carries that it belongs to what astronomers call population to stars. The oldest confirmed stellar population. The generation born from nearly pure primordial gas. No recycled material. No second-generation chemistry. Just hydrogen, helium, and the faint trace signatures of a universe that had barely begun. This is a star that formed as close to the beginning as physics currently allows. Closer, according to some measurements, than the beginning itself. And then something happened. In 2013, a team led by Howard Bond at the Space Telescope Science Institute published a refined age estimate for HD 140,283 using Hubble Space Telescope parallax data. The number they arrived at was 14.46 billion years, plus or minus 800 million years. The universe, under the most accepted cosmological models at the time, was 13.77 billion years old. The scientific community did not panic. Science rarely panics. What it did instead was more unsettling. It absorbed the number, noted the tension, and continued. The tension has not resolved. Subsequent measurements have refined both figures. The star's age has been nudged slightly downward. The universe's age has been nudged slightly upward. The error bars on both overlap, which is the technical condition that allows the paradox to be categorized as a problem rather than a crisis. But overlap is not resolution. Overlap means we cannot prove this is impossible. It does not mean we understand how it is possible. There is a difference, and no one talks about this enough. Let's be precise about what the age of the universe actually means. When cosmologists say the universe is 13.8 billion years old, they are measuring backward from the present, using the rate of cosmic expansion, the stretching of space itself that has been observed, quantified, and built into the Lambda CDM model. The model is the most successful cosmological framework in history. It predicts the cosmic microwave background radiation with extraordinary accuracy. It correctly describes the large-scale, structure of the universe as a web of filaments and voids. It works. And yet, the Hubble tension with separate but deeply related problem has emerged in recent years as one of the most stubborn and resolved conflicts in modern cosmology. Different methods of measuring the universe's expansion rate produce different answers. The early universe measurements and the late universe measurements do not agree. The disagreement is small in absolute terms. In scientific terms, it is alarming. What this means is that the number 13.8 billion may not be as settled as it appears in textbooks. If the universe is older than we currently calculate, even by a few hundred million years, a Methuselah star stops being a paradox. It becomes simply very old. Ancient. Exactly what it looks like. But if the universe is not older, if 13.8 billion holds, then something else has to give. Here's what that actually means. There are three exits from this problem. The first, measurement error. The star's age estimate carries uncertainty. The universe's age carries uncertainty. The overlapping error bars are doing genuine work, absorbing a discrepancy that may, with better instruments and more precise data, simply vanish. This is the clean solution. It requires nothing new. The second, stellar physics, we haven't fully modeled. Stars of this age and metallicity are rare. The models used to estimate their ages are calibrated against populations that are, by definition, younger and better understood. There may be physical processes, a convective mixing, helium diffusion, mass loss rates across billion-year timescales that are not fully captured in the models. A small systematic error in the physics could shift the age estimate meaningfully. These two exits are the scientific consensus. This is where most researchers park the problem. The third exit is rarely discussed in published papers, not because it's disreputable, but because it requires pulling on a thread that leads somewhere uncomfortable. What if the universe isn't as uniform as we assume? The age of the universe is not a measurement taken at a single point. It is inferred from the behavior of space across the entire observable cosmos. The lambda-CDM model assumes large-scale homogeneity that the universe, at large enough scales, looks the same in all directions, follows the same rules everywhere, expands at rates that can be averaged into a single figure. But the Hubble tension suggests this averaging may be hiding something. Different regions of space may have expanded at different rates. If the local universe, the region in which HD 140,000 to 183 formed and has lived its entire existence, expanded more slowly in its early history than the cosmic average, then time, locally, would have run slightly differently. Not differently in a science fiction sense, differently in a general relativistic sense. Space and time are not background constants. They respond to matter, energy, and the geometry of the region they occupy. In a region of slightly different early expansion, a star could be 14.5 billion years old while the averaged cosmic clock reads 13.8. This is speculative. It is not the consensus, but it is physically legal, and it points towards something that modern cosmology is quietly beginning to confront. The possibility that the universe is not as smoothly consistent as our models require it to be. HD 140,000 to 183 is still burning. It is a subgent now, a star exhausting the last of its core hydrogen, slowly expanding toward the end of its main sequence life. In a few billion years, it will swell into a red giant, then collapse. The star that was old before time had a name will become a white dwarf, cooling in the dark. We will not be here to watch it. What it has already done simply by existing, by persisting, by holding its age in its chemistry, like a preserved record, is something more than most discoveries accomplish. It has found the edge of our model and stood on the other side. Not dramatically, not with any announcement. It simply formed when it formed. It has been burning since. And when we finally looked closely enough to measure it, the number it gave us did not fit inside the box we had prepared. This is how the universe tends to work. We build a framework. We test it. It holds for a while, at the scales we can reach. And then something at the margins refuses to comply. Not violently, not with a clear signal, just quietly, persistently, sitting at the edge of what's allowed and not moving. The Methuselah star is not evidence that everything is wrong. The standard model of cosmology is not broken. The universe did not begin twice. But there is a star 190 light-years away that is, by the best measurements we have, as old as time or older. And the fact that we can hold that sentence without it collapsing into certainty in either direction says something about where we are. We are not at the end of understanding. We may not be as close to it as we thought.